Welcome to our class on chromatography. I had explained in detail about the introductory part of the chromatography in the last class. What I had told you was that the term chromatography embraces a family of closely related separation methods based on the observations of Dr. Michael Zweit and his experiments, which were done somewhere around 1903 to 1906. The importance of chromatography lies in its use as an analytical separation tool rather than the preparative technique. So, it serves as a means of resolution of the mixtures for the isolation and partial description of the components whose presence may be known or suspected. That means, you should know the components beforehand if you want to separate them. In chromatography, the components to be separated are distributed between a stationary phase and a mobile phase, and the mobile phase is a liquid, usually liquid or a gas, and stationary phase is a solid. The solid is loaded into a column in which it is fixed, and the mobile phase is allowed to percolate through the stationary phase. So, the mass transfer between the mobile phase and the stationary phase occurs either because the molecules of the mixtures are adsorbed on the particle surface or absorbed absorbed into the particle pores, or they partition into pools of liquid held on the surfaces or within the pores. This process is known as sorption. So, the sorption is the main technique which we use in chromatography. Separation of the components in a sample is based on the fact that rate of the travel of individual components is basically ruled by the mass transfer or partition coefficient of the molecules between the mobile phase and the stationary phase. The partition coefficient of each component determines the rate at which the sample travels. So, each component would be travelling at its own rate depending upon its partition coefficient. So, after some time interval, what happens is every component would be moving at different speeds, and they would be distributed in space over the stationary phase and subsequently emerge out of the column as a single component if the stationary phase is long enough to permit the total separation of the components. But you can have a variety of stationary phases as well as mobile phases. So, mobile phase you can have liquid, and the stationary phase also can be a liquid, and the corresponding technique is known as partition chromatography. You can choose mobile phase to be a gas. That means, you can pass a gas through a stationary phase and the stationary phase can be a liquid, and such a technique is known as gas liquid chromatography or GLC. You can have gas and solid, and the technique would be known as gas solid chromatography. You can change the mobile phase to liquid and stationary phase to an ion exchange resin. Then we can have ion exchange chromatography. Then another choice is you can attempt to separate the components according to their sizes, and this can be achieved by using the molecular sieves. So, if you use molecular sieves as the stationary phase and mobile phase as the liquid, then it is known as ion exclusion chromatography or gel permeation chromatography. If your mobile phase is liquid and your stationary phase is a thin layer of silica or alumina, then it is the technique is known as thin layer chromatography. You can choose to do the separations on paper like cellulose, and then if your mobile phase is liquid, you can have the technique is known as paper chromatography. So, all these techniques are possible and they have all been developed over a period of time, and many of the techniques which I have described earlier, gas liquid chromatography, gas solid chromatography, ion exclusion chromatography, and this gel permeation chromatography, all these things have reached a very high level of very high level of sophistication, and each technique can describe a chapter by itself. So, there are lots of things to learn, but it is important for us to know the important terminology of the gas chromatographic techniques, and the chromatographic behavior of a solute can be described either by its retardation factor or by its retention volume, that is VR. By varying the sorbent solvent combinations, you can and operating parameters, the degree of retardation can be varied over a wide range from nearly total retention to a state of free migration. You can either have total retention or in a state of free migration. All you got to do is you should be ready to change the mobile phase using different mixtures of solvents. So, let us define some technical terms related to chromatography. Here I am going to define firstly partition coefficient. So, partition coefficient is defined as Kd, and Kd is nothing but the ratio of the concentration of the substance which you are trying to separate into the stationary phase, that is denoted as Cs, and concentration of the same in the mobile phase, that is Cs by Cm. So, in most of the chromatographic papers, research papers etc., you would like to know what is the partition coefficient of this particular substance, and in a given system, that is for a given mobile phase and the stationary phase and for a given compound, the partition coefficient is defined. It would be its intrinsic property. Then secondly, we would like to define another term known as retardation factor. Retardation factor is basically defined as the distance travelled by the solute, that is the sample what you want to separate, divided by the distance travelled by the mobile phase. So, it is also defined in terms of the times spent by the molecule in the mobile phase and stationary phase. So, R is defined as Tm divided by Tm plus Ts, that is time spent by the component in the stationary phase, time spent by the component in the mobile phase, and the numerator is time spent in the mobile phase. In paper chromatography and thin layer chromatography, R is greater than Rf, that is retardation factor is greater than Rf by about 15%. That means, the solvent or the mobile phase would be ahead of the stationary of the solute phase by about 15%. Now, you can also define the retardation factor in terms of concentration Cm into Vm, that is concentration of the mobile phase multiplied by the total volume of the mobile phase divided by 1 minus R, that is concentration of the substance in the solute in multiplied by its volume. So, where Cm and Vm are the volumes of the mobile phase and stationary phase. So, R you can also define in terms of Vms only, Vm and Vs, that is given by Vm divided by Vm in plus Kd into Vs, because Kd we are going to introduce here. If you divide the top expression by Cm, you would end up with an expression something like this, 1 over 1 plus Kd into Vs by Vm. So, these are all different ways of expressing the retardation factor. So, another terminology that you come across very regularly is retention volume. So, in column elution methods, it is the amount of the mobile phase which has left the column at the instant the maximum of the solute emerges from the column. That means, when the substance leaves the maximum substance has emerged from the column, the amount of the mobile phase which has left the column corresponding to that is known as retention volume. At its peak, the maximum 50% of the solute has eluted in retention volume Vr, and 50% is retained in the mobile phase and stationary phase. So, we can write Vr into Cm is equal to Vm into Cm plus Vs into Cs, that is volume in the mobile phase multiplied by its concentration plus volume in the stationary phase plus concentration in the its concentration of the solute. So, you can simplify this again, Vr is equal to Vm plus Kd into Vs. Since Vr is also equivalent to the time that is retardation factor time multiplied by volume rate of the flow of the mobile phase, we can write Vr is equal to Tr into Fc, and Vr is equal to L into Fc by R mu, where L is the length of the column and mu is the linear flow rate of the mobile phase. Why I am introducing all these terminology is because you would be coming across many of these terminology in your whenever you are dealing with research papers. So, you can write Vr is equal to L into Fc multiplied by Vm into Kd, Vm plus Kd into Vs divided by mu into Vm. The ratio of L into Fc by mu is the volume of the mobile phase. The first term is called the first term means LFC into Vm is called the bed void or free column volume. It represents the retention volume of a substance that is unadsorbed or insoluble in the stationary phase, that is for Kd is equal to 0. Then we can define couple of other terms, that is column capacity. What is column capacity? It is the ratio of the concentration of the solute multiplied by volume divided by Cm into Vm, that is the concentration of the solute in the mobile phase multiplied by its volume. The volumetric phase ratio beta in a column is designated as Vm by Vs. So, we can write K is equal to Kd divided by beta. So, R is equal to, that is retardation factor, again we can write in terms of the K values 1 upon 1 minus K, or K is, you can solve this for K in terms of Vr and Vm, that gives you an expression of K is equal to Vr minus mu into Vm divided by Vm. So, the other factor that is important in chromatographic separations is the temperature effect. Usually, temperature effects are very important parameters in the operation of the columns due to the marked dependence of the partition coefficients on the temperature. For example, you can take a look at this expression Kd is equal to e to the power of delta S naught upon RT, minus e to the power of delta h naught divided by r t, that is approximately equal to a to the power of a e to the power of minus delta h naught upon r t. Here you should understand that delta S naught and delta H naught are the standard entropy and enthalpy of absorption. So, usually delta S naught is in the range of about 0 to 12 kilocalories, and that is at 20 degree centigrade. K D will decrease by about 50%. This leads a large value of R or large decrease in the retention volume. So, it is important for us to recognize the effect of entropy as well as the temperature. I hope you will appreciate the other terms in this equation, that is K D partition coefficient, R is the gas constant and T is the absolute temperature. Now, you can look at these figures. These are known as adsorption isotherms. That means, you can have different kind, when the molecule component is adsorbed onto the stationary phase, its concentration keeps on increasing, and the relation of the change in the concentration with respect to concentration and bed height is given by the adsorption isotherms. There are three isotherms, one is Langmuir isotherm and Freundlich isotherm, and other is linear isotherm. In Langmuir isotherm, we have the relation C s versus C d, that is it increases linearly and then it reaches a constant value. So, if you take a derivative in this thing, you would know that the slope is, you can determine the slope, and from the slope you can determine the adsorption capacity. Similarly, there will be changes with respect to other adsorbents. It need not be linear, but it can be linear also as shown here. So, different adsorption isotherms need to be plotted in chromatographic techniques usually, and these adsorption isotherms have a critical role to play in the development of the chromatogram. Now, what is a chromatogram? In the development of a chromatogram, the sample is generally introduced at the top of a column, and I introduce the sample into the column on the top. So, the liquid stationary phase is held in the column, and the mobile phase will be passing through, and I am introducing the sample through the column, and when the mobile phase is allowed to percolate through a stationary phase, the sample components develop into separate zones depending upon their retardation factor, and these zones you can call them bands or peaks. This is the development of different peaks and zones with respect to the time is known as chromatographic development. So, the development of the peaks are known as chromatograms. The development of chromatograms may be conducted either by frontal analysis or elution analysis or by displacement development. How do you really generate the chromatogram? That means, you have to plot the concentration versus time essentially. So, this can be done either by frontal analysis or elution analysis or by displacement development. We have three techniques to develop the chromatogram. So, what is frontal analysis? In frontal analysis, you will appreciate that we pass the sample solution continuously through the stationary phase or the absorbent. The active centers of the absorbents are occupied by the more strongly adsorbed components of the sample what you are passing through. That means, you have a column here and you are going to pass the mobile phase. Your mobile phase is the one which contains the components to be separated. So, mobile phase is continuously passing through the stationary phase, and the active centers will hold the components which you want to separate. So, the more strongly adsorbed components are held in the near the edge before in the beginning, and less strongly adsorbed components will be adsorbed later, and least strongly adsorbed components would be coming out at the bottom. So, they would be, that means they would be coming along with the travelling front. The solvent comes out first, followed by least strongly adsorbed component, followed by additional solutes which are more strongly adsorbed. That means, your chromatogram would be containing the peaks which are least strongly adsorbed component first chromatogram, the second peak would correspond to next strongly adsorbed component, and third would be the still more strongly adsorbed component. So, this is known as the frontal development. So, you can look at this figure how we are going to end up with a chromatogram. This is the concentration of the column effluent, and first comes out solvent, and then the least strongly adsorbed component, that is solute 1 and solute 2, then this slightly more adsorbed component, and then you will, if there is one more component, then you would be seeing solute 1, solute 2, solute 3 somewhere along this region. That means, the first peak will always correspond to only the pure solute. So, this technique is usually employed for the separation of the least strongly adsorbed solute. So, processes of this type are used for the removal of relatively small components of undesirable components when they are strongly absorbed. Suppose you have a solution of a substance in which some impurities are there, you want to separate the impurities, all you have to do is go for frontal development and pass the sample solution containing the impurity through a column, and the stationary phase would adsorb the impurities and lets out the other solute molecules which are least strongly adsorbed. So, the application of this would be always in the preparation of small components, and the mobile phase itself serves as the eluent. So, in elution development, that means now we are looking at the other aspects. Another method to separate is elution development. So, here what we do, again we take a small stationary, again we take a stationary phase like this, and then we pass the molecule solvents or solutes which are a mixture of substances to be separated. But here the solute mobile phase is not the same as the substance which you want to separate. As eluent is you are going to inject the substances which you want to separate, and then you are going to pass some other solution which will start pushing the components out of the column or through the stationary phase. So, here a small sample is introduced at the upstream end of the stationary phase. So, pure solvent now is called as eluent, and it is passed through the system which leads to a differential migration of the solutes in the mobile phase. Subsequently, the solutes will emerge out of the column depending upon the individual partition coefficients. If the partition coefficient is very low, then it comes out first. If the partition coefficient is very high, then it will be setting up several equilibria throughout the stationary phase and mobile phase, and it will come out later. So, if these are sufficiently different for different components, the mixture will automatically split into separate bands or chromatograms that migrate at different rates and emerge out. So, this is known as elution development. You can see a figure like this, that near the edge I have a substance, mixture of substances which I have injected, and then eluent is passing through like this, and over a period of time the eluents would be coming out 1, 2, 3, 4, 5, 6 like that, and then the detector also would give you a signal like 1, 2, 3, 4 and 5, 6. So, there is the chromatograms are always detected by using a detector. It can be an electronic detector or a specific detector which is chemically specific to the substance which you are separating. But what you can see here is the eluted substances are coming out one by one, and then after the first eluted compound, the eluent reaches the baseline, then the second one will start, then the third one, fourth one, etc. But the time in which they appear are also distributed in the same scale. So, elution development initially is like this, basically it is a mixture of substances A and B. After some time they separate out like this a little bit, and then if you permit enough time, that is denoted with a gap here, they would be separating from each other into different chromatograms, and then emerge out of the column as single components along with the eluent of course. So, this brings us to, this is another way of eluting. Here in the previous case, what we are having is the substance which is different from the substance you want to separate. That means, the solutes and the mobile phase are different. So, you have a choice of increasing the partition coefficient by the choice of different mobile phases, their mixtures, etc. But whereas, in the frontal development you have no choice, it just contains 1 or 2 impurities which you can pass through and column stationary phase and collect the purified substance. Now, the third one is displacement development. In this type of development, separation of the sample ingredients is achieved by running a more strongly adsorbed displacing agent through the column. That means, you are going to add all the substances and they get held up in the column. They do not come out, whatever is the eluent what you have chosen for the system, all of them will be held in the column. Now, if you want to separate them out, you have to push it through using a substance which is more strongly adsorbed. So, all the sample components have to be forced out of their sorption sites, and compelled to move ahead of the front produced by the displacer. In their turn, the sample components displaces each other. The first component, last component which is least strongly adsorbed will come out first, and then the second last will move to the last component, and then it will come out next like that. So, the first component which is most strongly adsorbed will come out last. So, you have a choice of choosing the mobile phases or varying the polarity of these molecule of the solvents for the separation of the components, solutes. This is known as displacement development. Here you can see I have given a graphical presentation. Here all the solutes are there, and then there is solute 1, solute 2, solute 3 and solute 4. Effluent volume is like this. Actually it should be eluent, but effluent is also fine. So, it comes out like this, and then once the displacer is there, all the 3 of them will be coming out individually one after another by occupying the sites occupied by the previous component which is adsorbed. So, it is a common practice to choose as displacer a substance that is closely related to the substances which you want to separate. Probably a higher homologue would do this job. So, if you want to separate butane, probably pentane will do the job, but if you want to separate pentane, hexane will do the job, something like a higher homologue. In this system, a rather heavy loading of the column is permissible. That means, you can take the substances can be in higher concentration. Therefore, this is useful for preparative work. That means, you can use it for industrial production also. Only thing is, you will have to scale it up to gram level or kilogram level, depending upon what you would like to achieve the separation. So, we can talk a little about the gradient elution. So, the gradient elution development is characterized by intentional variation of the eluting conditions during the course of separation. That means, they include composition of the mobile phase. You can change it, change the components. You can take 2 substances and keep on varying the composition of one another. That means, flow rates of 2 or 3 eluents, and that is one aspect. Second aspect is you can change the column pressure if you are using gas as a mobile phase, or you can change the column temperature during the separations, etc. In gas chromatography, this is very easily achieved by varying the column temperature and or the gas flow. So, in liquid chromatography, composition of the eluent is easily varied. So, the mobile phase with stronger displacing properties is continuously run through the column. Thus, the zones are forced more closely together whenever you are changing the mobile phase. So, if the mobile phase is becoming rather more polar, the chromatograms will be forced nearer each other, because they will be coming out much faster than the eluent. So, the zones are forced more closely together and they become narrower. Several solvent mixing devices are available today for efficient separation of the solutes. You can choose solvents which can vary the through several containers, and you can vary the composition of one solvent with respect to another on a continuous basis also. So, such efficient separation can be obtained if you have the capability or interest in separating the substances which are held very strongly. So, the dynamics of chromatography, let us discuss a little bit about the dynamics, that is, let us talk about efficiency. The measure of the column efficiency is expressed by what is known as plate number. The notation is N and it is given by 16 multiplied by V r divided by W whole square, or 8 times V r by W square. whole square, where W is the width of the elution peak measured in the volume units, that is how many times the width is from the volumes employed, or W e is the width at C max maximum concentration, or 0.368 times C max concentration max. C max is the defined concentration of the material in the effluent at its peak maximum. So, if you know the C max, you can determine the plate height, that is you know the column diameter, you know the VR, and you know the WE. So, column elution curves and terminologies can be defined like this in terms of this curve. Here I have plotted concentration of the solute in the effluent on the vertical axis, and this is the point of injection, that is here. For standardizing the chromatogram, I am introducing a small gap, and that is known as air peak. That means nothing will come out, but there will be a small peak which will tell me that the chromatogram has started. And then I have one peak and second peak, third peak, etc. And the distance from the air peak to the middle of the first chromatogram peak is known as VR dash. Similarly, VR 1 dash for the second substance, etc. And this would be VR 2 dash, that is for the third substance. So, VR dash, VR 1 and VR 2, etc. we can define, and the axis is volume or time axis. So, you can see in this case the width of the column, width of the chromatogram is very well defined, whereas in this case there is some amount of overlapping of M1 and M2 in this case. So, this tells us that there is some more work is required to separate the mixtures completely. So, the retention volume may be replaced by retention time and width also by time. Under ideal conditions, the chromatogram approach is a Gaussian curve. If you remember the previous figure, this is basically a Gaussian figure. All these figures are Gaussian figures. That means, with a simple lambda max and then separating each other well after the median. So, the chromatogram approaches a Gaussian curve only under ideal conditions, and the width would be 4 sigma, that is the standard deviation. Basically, plate number compares the narrowness of a peak to the length of the time, that is TR is equal to VR by FC, and the component, that is the component has been in a column. So, plate height H is the length of the column divided by the number of plates, that is sigma squared by L. Now, we can talk a little bit about zone spreading. When a mobile phase boundary passes the solute zone, the rate of sorption and desorption cannot keep pace with that of the solvent, because the solvent would be running away faster. That I have already told you that it runs about 15%, 0.15% more than the solute front. So, the progress down the column by individual solutes resembles a random stop, and it is basically a stop and go, stop and go, stop and go process. The net forward travel of each component is actually an average value, and there is a normal dispersion of values around the mean. That means, like when the curve is coming like this, the mean value, there is always a normal distribution. Further, the solutes initially occupy a number of plates. The effect will be that a number of chromatograms are started successively which lead to zone width. The separation occurs, but they are not very well separated, but the number of separations always leads to zone banding. So, zone spreading is considered to be due to a series of molecular diffusion processes, and local non-equilibrium processes also will take part, originating in the velocity inequalities. Velocity will be different. So, all these processes or molecular diffusion and non-equilibrium patterns result in the inequality of the flow pattern for the different components, but the extent of spreading is governed by diffusion between the fast and slow stream paths. What we are trying to say is zone spreading is considered to be a molecular diffusion and non-equilibrium processes, which leads to velocity inequalities. The extent of the effect what you see in the chromatogram is governed by the diffusion between the fast and slow processes. The result is different and the cause is different. Result is seen, but cause is molecular diffusion and non-equilibrium patterns. So, the resolution again, the degree of separation is always a problem common to all chromatographic methods. In truth, complete separation of a substance can never be achieved. There is always a small catch when people say that I have separated totally 100%, it is never possible. So, in truth or in theory, complete separation can never be achieved because a chromatographic peak approaches in shape a Gaussian distribution, it never reaches the base value. In actual practice, minimization of the degree of overlap or cross contamination, minimization of cross contamination also between the adjacent zones to a desired experimental level, that is aimed at. If you are able to see well separated chromatograms, one would say that the experiment is fairly successful, but no amount of separation can achieve 100% result in chromatography or for that matter any other process where separations are aimed at, because it is always a process of the separation of the substance in the, it is a partition process in the stationary phase as well as in the mobile phase, in the mobile phase as well as in the stationary phase. So, the resolution is therefore essentially a measure of the degree of the separation processes. It is never an absolute value. Mathematically, we can write something like this: RS is given by delta z divided by 4 sigma, that is 4 times the standard deviation. So, where delta z is the separation of the zone centers, and for column elution methods we can write something like this: VR2, that is the second component, VR1, that is first component, divided by 0.5 times width of the second peak plus width of the first peak. So, the resolution is influenced by the relative retention ratio and it is influenced by partition coefficients ratio, it is influenced by plate number, it is influenced by column length. So, resolution is never a one way traffic, it depends upon so many factors which are basically at variance with each other. So, elution is generally continued until all the compounds have left the column. This permits the reusing of the column, because once you are able to separate the components, you should be able to reuse the column. So, the analysis of column effluent can be done by any method suitable for continuous analysis. That means, the column effluent needs to be monitored, and you can monitor the column effluent whether it contains the component or it is pure mobile phase. If the substance contains the component, if the eluent contains the component, then the component can be analyzed by spectrophotometry, refractometry, polarography or any other radiochemical methods, infrared, so many other ways. But the moment you see the substance is not responding to any of the analysis technique, you can be fairly sure that the eluent has become pure and the components have left the column. That is the signal for you to restart another experiment. Till that time, you are not sure whether the column can be reused or not, whether the separation has been achieved or not. Frequently, automatic equipment is employed in conjunction with fraction collectors also. Suppose the components are very valuable, then you would like to collect the component, and you would also like to record the substance, the chromatograms. Therefore, ideally the property chosen for monitoring the eluent should be linear function of the solute concentration. A very simple and straightforward assumption, that is, the substance what you want to determine should be a linear function of the solute in the solvent, that is mobile phase, and the detector response should also be linear with respect to the component that is being separated. That is the ideal condition. So, quantitatively the total amount of a solute eluted is measured by the area under the chromatogram under a peak, or you can use the area under a peak or peak height, or you can even record it on a piece of paper, cut the graph paper and weigh the paper. That is one of the very well known quantitative techniques used very regularly about 30-40 years before. So, that is known as quantitative chromatographic analysis. If the separation is achieved properly and the chromatograms are well developed, well separated from each other, the peak can be weighed directly. Now, I am talking about fraction collection. That is, a fraction collector, what are their jobs? Their job is to enable the elute to be collected in portions as desired and permits one to characterize various species present in each fraction by independent methods. These are basically based on the lapse of equal interval of time. That means, you can collect the sample at equal interval of time and then analyze them, or you can go for constant fraction size. You can say I will collect only 10 ml of the sample every time and then I will analyze the samples, or you can say the detector output or drop counting, I will collect after every 100 drops, whatever comes I will have number of fraction collectors. So, a high degree of automation is possible in all these cases. That is the advantage of fraction collection, and several other components can be analyzed in this way. So far, I have given you a glimpse of the chromatographic techniques, and now I would like to move on to gas chromatograph, which I would like to deal in more detail. Other chromatographic methods are also there, and they can be very easily given the technical input, that is terminology and plate height and other chromatographic terminology. you can go through them and then adopt a suitable technique for your presentation, for your work also. But what I would like to discuss with you is about the gas chromatography. Why I have chosen gas chromatography is because it encompasses almost all the principles that we have discussed in chromatography in one single technique. Therefore, I would like to go slightly in more detail with respect to gas chromatography and also introduce you to the tremendous advances that have occurred in the gas chromatographic instrumentation, gas chromatographic development, and then with respect to methods development. So, it represents one of the most important development in chromatography, which has been overtaken only by high pressure liquid chromatography, that too only since last 20 years. So, gas chromatography represents almost all the parameters that one would like to learn at this stage. Now, let us see what is gas chromatography in detail. So, the gas chromatography differs from other forms of chromatography in that the mobile phase is a gas. That means, you have to pass the gas through a column continuously from a cylinder preferably, and the components are separated as vapors, they are not separated as liquids. The separation is accomplished by partitioning the sample between the gas and a thin layer of non-volatile liquid. Thin layer of non-volatile liquid which is coated on a solid phase. That means, the stationary phase contains two components. One is a stable support phase on which a liquid is coated as a thin film. So, it is known as gas liquid chromatography. A sample containing the solutes is injected onto a heated block. Why heated block? Because the sample has to be vaporized also in the form of respective vapors, and that should be mixed with the gas which is we are using as a mobile phase, and it is swept as a plug of vapor by the gas, and the gas we call it as carrier gas. So, we have three components in gas chromatography. One is the carrier gas which serves as the mobile phase, and your sample which should be converted into a vapor which will be swept away into the column by the incoming carrier gas, and it will be swept away as a plug of vapor, and the solutes are separated by the stationary phase and then desorbed by the fresh carrier gas. The moment the plug of vapor passes through the stationary phase, it gets separated according to the partition coefficients, and the mobile carrier gas is forcing the sample, that is the vapor is getting sorbed and desorbed, because there is a continuous pressure of the gas coming through the stationary phase. So, the fresh carrier gas serves to desorb the components of the gas. Now, elution method of gas chromatography is something like this, that is I have a column here and the sample is here A plus B. I have a packed column, and in this column you can see the small particles on which liquid is coated, but that is not visible, and the sample is introduced from the top. And then I have the packed column, gas is passing through, and then this plug will start moving at its own speed and depending upon the partition coefficients, and then it passes on and on and on and on. Here the separation is almost complete, here they are well separated, and here one is eluted, sample A is eluted, and here sample B is being eluted. So, the detector signal will always show, if you place a detector somewhere here at the end of the column, it will show you a basic straight line, that is from the mobile phase, and then component A is coming out and then followed by component B is coming out. This is how the separation of gas chromatography, separation of the components occurs in the gas chromatograph. Now, the process of separation in each is repeated in each plate as the sample is moved towards the outlet, because we know that the gas stationary phase can be represented as number of theoretical plates in which the separation will be taking place. So, as the in each plate the sample gets adsorbed and then gets desorbed, moves on to the next plate, again it gets adsorbed and desorbed, and then like that it will be continuing throughout the column. So, each solute will travel at its own rate through the column, and the bands will separate into distinct zones depending upon the partition coefficients and the band spreading. The solutes are eluted one after another, as I have told you, and we will continue our discussion in the next class how we can detect a series of signals resulting from the concentration changes and rates of elution on the recorder as a plot of time versus the composition of the carrier gas stream.